Okay, so welcome to the next class in probability. So today we'll start talking about dependence of random variables. So in a lot of the exercises and a lot of the things, you usually take x, y, which are independent random variables. So this is not always the case. And let's look. Okay, so from now on, in this class, we'll forget about the concept of independence for a second. So we're just gonna take two random variables, and we're going to see how they can be related to one another. So let's start with an example in which we roll one dice, and of course our sample space here is 1, 2, 3, 4, 5, and 6. And here we're going to consider x, which is the random variable given by the indicator of the number omega is even. And we are going to consider y to be the indicator of omega bigger or equal than 4. Okay, so this can actually just see as an event, but we could also just see this as, okay, so if we look at x, if we look at the distribution of x, so we have that the probability that x is equal to 1 is going to be equal to 1/2, okay, because in this case we can take omega to be 2, 4, and 6. The probability that x is equal to 0 is also equal to 1/2, and this is omega equals to 1, 3, and 5. Okay, so what we can say is that x is distributed with as a Bernoulli random variable with parameter 1/2. So similarly, we can look at for y. So the probability that y is equal to 1 is going to be equal to 1/2. Okay, this is omega equals to 4, 5, and 6. And the probability that y is equal to 0 is also equal to 1/2, and this is equal to omega 1, 2, and 3. Okay, so again, this y is distributed as a Bernoulli random variable with parameter 1/2. But what we can check is that x is not independent of y. So in particular, if we look at the probability that x is equal to 1 and that y is equal to 1, this is going to be equal to this is going to be, so x equals to 1 means that w is even, and y equals to 1 implies that w omega is bigger than 4. So what we're going to have is that this is equal to 1/3, which corresponds to omega being equal to 4 and 6. Okay, but this is different from the probability of x is equal to 1 and times the probability of y equals to 1. Okay, so these guys are not independent. But what we can actually see is that when there is no independence, we can still look at the joint mass function. So let's look at the joint mass function, and then we'll do a definition. So we can actually consider x and y as these two different random variables, and now we can consider a joint mass function f of x, y, which is going from R2 to 0, 1. This is the joint mass function in such a way that what we're going to define fxy of little x, little y is going to be the probability that x is equal to x and y is equal to little y. So in particular, so these are discrete random variables, so we can only take 4 values. So we can look at f of x, y for arbitrary x and y. This is going to be 1/3 when x is equal to 1 and y is equal to 1. Then we have to look at the probability of x equals to 0, y equals to 1. So in this case, the number is bigger than 4, but it's odd, so this is just equal to 1/6. Now the probability that x is equal to 1 and y is equal to 0. So here we have that the number is less than 4 and it's even, so it's also again just 1/6, and the probability that x is equal to 0 and y is equal to 0 has to be again 1/3. Okay, so this is 1/3, 1/6 for x equals to 1, y equals to 0, 1/6 for x equal to 0, y equals to 1, and it's equal to 1/3 if x is equal to 0 and y is equal to 0, and it's 0 otherwise. Okay, so this is the joint mass function on all of f of x and y, and similarly, okay, so just as a definition, given x comma y random variables, f of x, y from R2 to 0, 1 is the joint mass function if only if f of x, y of little x, little y is equal to the probability of x equals to x and y is equal to y. Okay, so these are discrete random variables. So let's put discrete so that we actually have a pointwise value for this guy and we don't have to be actually integrating. So similarly, it's an observation. This is not as useful, but it's similar to what we have done before. So an observation is we can also define the joint distribution function, which is f of xy, capital F of xy, which is also growing from R2 to 0, 1. And in this case, we define it by f of xy of little x and little y is equal to the probability that x, the capital X is less or equal than x, and the capital Y is less or equal than little y. Okay, so we're not going to do much with this, but the point is you can define this, and this has similar properties, has similar continuity properties to the single random variable case. Okay, and this is an if and only if, the same as we have seen before, but for a single random variable. Okay, so just to have a notion of independence, just let's say, look at the following lemma. X and y are independent if and only if the joint mass function f of x, y, x, f of x, y at x, y is equal to the marginal at x and the marginal at y. Okay, so this is the joint distribution, joint mass function, and this is the mass function for x, and this is the mass function for y. So an observation would be that more in general, we only need a decomposition into products. We only need a decomposition into products, and then they have to be actually the marginals. Okay, and this is valid for every little x and little y in R2. Okay, I'm not going to do the proof of this, but morally, okay, so the proof is similar to things that we have seen before. So this is the probability that x is equal to x and capital Y is equal to y is equal to the probability of x is equal to x times the probability of y equals to y, and this is if and only if x and y are independent. Okay, but this thing here is the joint mass function fxy, this is fx, and this is fy. Okay, and that's just an observation. Okay, so but one of the interesting things is that sometimes we might have access to the joint mass function, but we're interested in getting the marginal. So we might only have access to the joint mass function, but we are interested in calculating the mass function for one of the variables. So one of the random variables. So in this case, so if we want to find what is the probability, so if we want to find fx of x, this is just the probability that x is equal to x, but this event can be decomposed into a lot of different events that are disjoint, which is, so x equals to x is equal to the union over all the values y of the set x, capital X is equal to little x, intersection capital Y is equal to little y. Okay, so this is a disjoint union. Okay, so then by the actions of probability, this is the sum over little y of the probability of x equals to x and y is equal to little y. But then this is just the sum over y of fxy xy. Okay, so this here is called the first marginal of fxy. Okay, so in this case, if we sum over all the values, all the possible values of y of this joint mass function, we actually find the mass function for capital X. Okay, so in the example, and okay, so similarly, fy of little y is going to be the sum over x of f of xy, x comma y. Okay, so let's look at the example we had seen before. So the previous example. In the previous example, we had that f of xy was equal to 1/3, x equals to 1, y equals to 1, 1/6, x equals to 0, y equals to 1, 1/6, x equals to 1, y equals to 0, and 1/3, x equals to 0, y equals to 0. Okay, so one of the things you should notice, which I didn't say here, I guess I could put it as an observation. The sum over x of the sum over y of f of xy has to be equal to 1. Okay, so similarly as we are saying the union over all the possible y's is going to be the probability of x equals to x. Now if we sum over x and we have the union of x equals to x and y is equal to y, if we have this double union, this is going to be the full set. Okay, so the union over x of the union over little y of x, capital X is equal to little x, intersection y is equal to little y is going to be the full set of omega. Okay, so and this is a disjoint union, so you can actually find that the sum of all the values of the joint mass function is actually equal to 1. Okay, anyway, so if we sum all of these values, we get 1. And that's an easy check to say if you have gotten the right distribution function, the right mass function. So if we want to calculate f of x of 1, we have to do the sum over y of f of xy of 1 comma y. Now, in this case, this is just going to be f of xy of 1, 0 plus f of xy of 1, 1. Okay, so this is equal to 1/6 plus 1/3, which is equal to 1/2. Okay, and this is exactly the probability that x is equal to 1. Okay, this is what we shown before. So here we have x, which is Bernoulli with parameter 1/2, which matches exactly this. Y is also Bernoulli with probability with parameter 1/2. And so here what we have is a pairing between x and y, which is not independent. Okay, and so you can write this f of xy in such a way that they are not actually independent. Okay, so if they were independent, all of the values here, if x comma y are independent, then f of xy has to be equal to 1/4, 1/4, 1/4, and so on. Okay, so this is in the case of Bernoulli variables. So we can see that this is a different coupling between these variables. Okay, so let's talk a bit about correlations. I'll be a bit fast, but this is just for you to have the idea if you ever have to talk about like normal people about what you've been studying in probabilities. So we can start talking about correlations. So here, I mean, just to take a simple example. So let's say that x is the height of a person and y is the weight of a person. So if we pick a random person from a city, what we're gonna see is that if x is larger, then y is probably larger. Okay? So whenever x increases, we are going to expect that the weight of the person increases. Okay? This is not true in general. It's not true for every person, but it should be true in a statistical sense. So the correlations and the covariance that we're going to define, in some sense, measure what is the correlation between x and y. So can we say that when x grows by 1 unit, do we know that y also grows by 1 unit, or do we have to normalize, or these kind of things? So let's do a couple of definitions. I'm not going to give many examples. So the definition of covariance between x and y is going to be the expectation of x minus the expectation of x times y minus the expectation of y. Okay, so these parentheses, let's put it as a square bracket, goes here, and there is a multiplication. Okay, and if we use the properties of the expectation, we get that this is the same as the expectation of xy minus the expectation of x times the expectation of y. Okay, so one thing to notice, so an observation, is just that the covariance of x comma x is literally just what we defined before as the variance of x. Okay, so one of the things covariance is measuring, so the changes in x, how do they affect the changes in y? So if x is larger than its expectation and goes up, what is happening with the changes in y? So if on average x is going like over the expectation with respect to y is going under the expectation, then we would expect that the covariance is negative, and then we would expect that x and y are negatively correlated. So, okay, so whenever x grows, y actually decreases. Anyways, but the problem is that covariance doesn't have so let's how can I put it? So covariance is not normalized. So you cannot actually talk much about like covariance if you have to put it in the right units. Okay, so x and y have to be normalized somehow. So the way to normalize the covariance coefficient, so normalizing the covariance coefficient, the covariance, we have the correlation coefficient, which apparently is denoted rho of xy, is going to be the covariance of x comma y over the square root of the variance of x times the variance of y. Okay, and this has is a-dimensional. A-dimensional. Okay, so it's a coefficient and has no units. Okay, so this the dividing by the variance of x and y actually has no units. Okay, and this is something I'm not going to show, but it follows from the it follows from the Cauchy-Schwarz inequality is that the lemma is that rho minus 1 is less or equal than rho, which is less or equal than 1, and rho is equal to 1 if and only if there exists A, B, C non-trivial such that the probability that AX plus BY is equal to C is equal to 1. Okay, so what would be the idea here? So what we are saying is that of this correlation coefficient is that it's a number between -1 and 1, and can only be -1 or 1 if we have some linear relationship between x and y. So the linear relationship is morally saying that x is equal to b over a times y plus c over a. Okay, one has to be careful with the non-triviality of the parameters, so you cannot necessarily always do this. But the idea is that x is a linear function of y. Okay, so in particular, if rho is equal to 1, this coefficient is going to be positive, and if rho is equal to -1, this coefficient is going to be negative. So this rho is measuring what happens when x increases by 1 unit. What is happening? How is y increasing? Is it also increasing by 1 unit or not? Okay, so if you have rho positive, it means that they are positively correlated, and if you have rho negative, it means they are negatively correlated. So here, in the height and weight of the person, we expect rho to be bigger than 0. Okay. And I guess something I didn't say, but should be an observation is, okay, so from the things that we have seen before, so if x, y are independent, then E of x, y is equal to E of x times E of y, which implies that the covariance x, y is equal to 0. Okay, so this would be a lemma or some proposition. If x and y are independent, then the covariance is equal to 0. Okay, so this correlation coefficient is also measuring if the x and y, what is the correlation between x and y. So in particular, when they are independent, they are not correlated, which implies rho is equal to 0. So x, y independent implies rho is equal to 0. Okay, so I haven't done the computation, but in the previous example, if we check this, I would expect to see that x and y are actually positively correlated, because when x is 1, when capital X is equal to 1, y is more likely to be equal to 1 than 0. Okay, so you are expected, I'm expecting that there is a positive correlation between these two things, and you can actually check that. Okay, so just as a last thing for joint variables, okay, one of the things would be, I did this for 2 variables, but you can generalize, can be generalized to 3 variables. or more. Here what I'm meaning is the 3 random variables. Here what I'm meaning is the mass functions. Okay, not for the covariance, but for the mass functions. Okay, so one last thing. Let's look at sums of random variables. Okay, so if we define z, which is equal to x plus y, we need access to the joint distribution f of x, y to compute the mass function for z. So in particular, if we look at f of z at a particular value little c, this is going to be equal, okay, so this is equal to the probability that z is equal to little c, but this is the same, or I mean, can be seen again as we were saying before, this is the probability of all the possible values of x, so the union of x is equal to x, comma, union of x equals to x, and z is equal to little z. Okay, so we are writing this event as a disjoint event of the values of x, and so for this case, we can write z in terms of x plus y. Okay, so in this case, this would be the sum over x of the probability that x is equal to x, but z is equal to c is the same as y is equal to z minus x. But now, if we have access to the joint mass function, this is equal to the sum over x of f of x, y of x, z minus x. So for a fixed value z, the way that we can find the mass function for the sum is by taking the sum over x of f of x, z minus x, and similarly, this is the sum over y of f of x, y of z minus y, comma y. Okay, so this is the same, just by symmetry. This is by symmetry. Okay, so this formula seems a little weird, but if x comma y are independent, okay, so this is an if and only if f of x y is equal to f of x times f of y, so then f of z at little c is going to be the sum over x over of fx at x times f of y at z minus x. But this guy here, if you're used to seeing, you're probably used to seeing with the full integral, is just the convolution of fx fy applied at z. Okay, so this is the what is called the convolution of two functions. Okay, so this thing here was just to connect with the convolution, which is something you'll see later on if you're doing math. Okay, so let's finish this class with a couple of things on the expectation and variance. So one of the things is why are we so interested on the expectation of x and variance of x. So one of the things I said in one of the first classes is, so let's say that xi, and now we're going to have, so x1, x2, x3, x4, and so on are independent, equally distributed random variables. Okay, so xi could be Bernoulli 1/2, which is flipping independent fair coins. Or xi could be whatever else you can think of, but this is the example I did in the first class. So the central limit theorem tells you that the sum of xi, so there is a couple of things. The sum of xi from I equals to 1 up to n, 1 over n, this is what we're calling Sn, converges to the expectation of x1. So x1 just being one of them, they're all independent and equally distributed, so they all have the same, which is equal to E of xi for every I. Okay, so this is when n goes to infinity. We can actually see that the mean behavior of these variables is going to be just equal to the expectation. Okay, now the second order is the central limit theorem. This is the law of large numbers. And the second order is the following. So if we take square root of n of the difference between Sn minus the expectation of x1, we are going to see that this is converging to a Gaussian random variable with 0 expectation, but with the parameter variance of x1, okay? And this is central limit theorem. Okay, so what this is telling you is that if you rescale, by rescaling, we have Gaussian behavior. Okay, so if you look at this guy, this will become a nice Gaussian, which is centered around 0, and the variance, which measures how fat or flat the Gaussian is the variance of x1. Okay, so understanding these things is a good idea, because these are the basis of a lot of statistics that are out there. Anyways, and so the point is that sometimes, as we've seen before, it's actually easy to calculate the expectation, and this is related to something that we want to do in a particular theorem. So, okay. Okay, so let's look at a couple of observations of these things. So if we have x which is less or equal than y, then we have that the expectation of x is less or equal than the expectation of y. So how do you actually show this? You can check that, so y minus x is a positive random variable, then the expectation of y minus x is bigger or equal than 0. Okay, so this is by previous proposition. Okay, proposition in the previous class. Okay, so in particular, we can write y as x plus y minus x. So then the expectation of y is going to be the expectation of x plus y minus x, which is equal to the expectation of x. So the expectation you don't need independence or anything to separate in the respect to the linearity. So this is the expectation of x plus the expectation of y minus x. But this, as we've just seen, is bigger or equal than the expectation of x, which is what we wanted to do. Okay, so in a sense, sometimes it's easy to see, like, bound a random variable by another by below, which has a much easier expectation to calculate. So then we can use this trick to see that to bound the expectation. And maybe if you have a sequence of these guys, you would expect perhaps the bound to get tighter and tighter and try to actually get equality on both of them. So another quick observation would be, so let's put 1. The second, if x is the indicator of a set A. So this is similar to what I did at the beginning of the class. So A is a subset of omega, where A is in the set of events. So what happens if we take the expectation of x? The expectation of x is the probability of A. Okay, so sometimes it seems like a really convoluted way, but it's easier to find the probability of A by computing actually the expectation of x. Okay, so this is similar to how your monitor has done some of the exercises by showing what is the probability of a certain event by looking at the expectation of the associated random variable, which is an indicator over that event. Okay, so what are some important tools to know from using expectation and using expectation and variance? One of them, the following theorem, which is called Markov's inequality, says the following: let x be a non-negative type random variable, then the probability that x is bigger or equal than A is less or equal than the expectation of x over A for every A. Positive. For every A positive. Okay, so if you have an expectation which is small, then you can actually bound what is the probability that x is larger than 100. So if you have that the expectation of x is equal to 1, then the probability that x is larger than 100 has to be small. It has to be like less than 1 over 100. Okay, and so how do we prove this? The proof is by observing that x is bigger or equal than x times the indicator of x is bigger or equal than A. Okay, so this is like the indicator of A. And moreover, so x is larger than this because, okay, so this here is because x is non-negative. Okay, and in particular, over the set, over the indicator x bigger or equal than a, this is also bigger or equal than a times the indicator of x bigger than a. So, in particular, by the observations we saw before, the expectation of x is bigger or equal than the expectation of a times the indicator of x bigger or equal than a. But now, using the properties of the expectation, the linearity of the expectation, we can take a outside, and we can use the property that we saw before, that the expectation of an indicator is the probability over the set. So this is just equal to a times the probability that x is bigger or equal than a. Okay, so let's look at an example. So this is just to get an idea of how the Poisson distribution behaves. So if x is Poisson with parameter lambda, so one of the things that we have is that the expectation of x is equal to lambda. So then what is the probability that x is bigger or equal than 2 lambda? Okay, so this parameter lambda basically is measuring how far are you from bunching up at 0. Okay, so the bigger the lambda, the bigger that your x is being distributed. So the larger the variance as well. So in this case, what we have is that the probability of x bigger or equal than 2 lambda by the previous by the Markov's inequality is going to be less or equal than the expectation of x over 2 lambda. But the expectation of x is equal to lambda over 2 lambda, which is exactly equal to 1/2. Okay, so the probability that you are actually bigger than 2 lambda is less than half. So most of the mass, so the probability that x is less than 2 lambda is bigger or equal than a half. Okay, so the smaller the parameter lambda, the more accumulated close to 0 you are. Okay. Okay, so another way of using this Markov's inequality is by, so I think this is what people call Chebyshev's inequality. So one of the things is that variance measures deviation from the expected value. Okay, so let's look at the following theorem, which is similar to what we were saying before. Let's call this is Chebyshev's inequality. And says, okay, the probability that x minus e of x is bigger or equal than a is less or equal than the variance of x over a squared. Okay, so one of the things we should notice is that here we have power 1 and here we have power 2. Okay, and this is actually fairly important for larger values of a. Okay, So this thing here actually matters, and let's look at the proof, and then we'll actually see that we can actually put, if we put here the expectation of x squared, here we are allowed to put a squared. And in general, if we put any expectations of a function of x here, here we can put f of a. Okay, so let's look at the proof of this. So the probability that x minus ex is bigger than a is equal to the probability that x minus ex squared is bigger or equal than a squared. But by this is less or equal by Markov's inequality, this is bigger or equal than the expectation of x minus ex squared over a squared. But this is just equal to the variance of x over a squared. Okay, so in general, if f, that's how we call it, if g is, and so this is a function g r that is going from r to r, is increasing, okay, so then the probability that x is bigger or equal than a is going to be the probability that g of x is bigger or equal than g a, which is going to be less or equal than the expectation of g of x over g of a. Okay, by Markov's inequality. So the idea in general for Chebyshev or just anything, so if you have that the expectation is finite for a function g of x, so here g could be taking x squared as we've done before, taking x to the cube, x to the 5, or whatever. So having finite moments for x, so basically taking the expectation of x to a certain power being bounded, also implies that the probability that x is really large decreases really fast. Okay, so the larger the exponent in g of x, the larger that this probability is going to 0. Okay, this is of course always assuming it's finite. Okay, so it could be that the expectation of x squared, the expectation of x is finite, but the expectation of x squared is not finite. Okay, and then we'll actually see later on some examples of that. So yeah, anyways, this is for you to take in mind, but this is just two useful inequalities which you're going to use in a lot of places.